All right, howdy class. So I want to start by showing you this flow chart again, and I want to walk you through how to use it. So in chapter 8, we learned about stoichiometry for the first time, and we started by just doing moles of A to moles of B, and you multiply by the stoichiometric ratio or mole ratio, like we do every time. To go from one substance to another, we have to use those mole ratios, meaning we have to have a balanced equation. Okay, so from there we got a little more complicated where we started with grams and wanted to go to moles, or we started with grams and wanted to go to grams. So in that case, grams of A to turn into moles of A, you have to multiply by 1 over the molar mass. So you put the grams on the bottom and the moles on the top so that grams will cancel out. You get to moles of A, you'll use your mole ratio, and that'll get you to moles of B. And then if you need to go to grams of B, you're going to multiply by the molar mass, so grams on top this time, moles on the bottom, so we can cancel out moles, and get to grams of B. So uh, this was our stoichiometry process when we were looking at chapter 8, when we were just talking about grams of something and grams of something else. So that process goes like this. But now we can do something else. Now we can talk about volumes and concentrations. So now we have a little more to work with. So volume or volume. Or we can go from grams to volume or volume to grams as well. So if we have a question that asks us how many or what is the volume, how many milliliters, I guess, of something, HCl, I guess, do you need to dissolve X grams of calcium carbonate? So you would be given a number of grams of calcium carbonate. Oops. So you'd start here. That would be your A. You would have you'd have your balanced equation, which would give you this mole ratio. So you need to go from grams of A, grams of calcium carbonate, to moles of calcium carbonate. Always need to go to moles before we can go to some other substance. Then we use our mole ratio to get moles of B. So this would be our moles of HCl. And we want to find a volume. So we're going to divide by concentration. So moles of something, moles of B or moles of HCl, divided by the concentration, divided by molarity. So M is moles per liter. So if we divide by it, we're going to have liters over moles. Moles cancel out, and we end up with a volume in liters. If we need to convert it to milliliters, we can, but we got our volume. So we went from grams to volume. You can do the opposite. You can say what mass of calcium carbonate do you need to use up all of your hydrochloric acid, or to like neutralize your hydrochloric acid. Then you would start with a volume of hydrochloric acid and do the opposite. You'd go up this way instead of going to the right and down, you'd go to the right and up. So this flowchart is going to be super helpful for you. You don't need to memorize this. You just need to know these conversion factors. So if you have grams of something and you need to convert it to moles of something, you multiply by 1 over the molar mass. So molar mass is your conversion factor. If you have moles of something and you want to get grams of that something, you multiply by the molar mass. So again, molar mass is your conversion factor. You multiply here, divide over here. If you want to go from a volume to moles, you multiply by the concentration. So volume cancels out, volume in liters cancels out. If you want to go from moles to volume, you divide by the concentration so that moles cancel out. So concentration is your conversion factor between moles and volume, just like molar mass was our conversion factor between moles and grams, or moles and mass, we should say. And our mole ratio will always be our conversion factor between two different substances. Okay, so these are your conversion factors you need to remember. You don't need to remember this flowchart, but you should remember how to convert from grams of something to moles of something, and then from moles of that thing to moles of something else, and back to grams or to a volume. All of your stoichiometry problems are going to be like that. You're always going to be asked about grams or volume of one substance, and you'll need to use your balanced equation to convert to moles of the other substance and then go to grams or volume of that substance. Okay? This will be your roadmap for all of these problems. All right, so let's practice some of these problems. Sodium carbonate is available in very pure form and can be used to standardize acid solutions. What is the molarity of an HCl solution, hydrochloric acid solution, if 32.0 milliliters of the solution is required to react with 0.364 grams of sodium carbonate? So we are reacting, so we want to write a balanced equation. That's always our first step if we aren't given a balanced equation, to write that balanced equation. So we've got sodium carbonate and HCl. So what are we going to make? So this is going to be a double displacement reaction. Most acid-based, not acid-based, but acid-based reactions are those double displacement reactions. Acid-base reactions are too. I'm just saying if there's an acid and you can't really identify if this guy's a base, but you know this one's an acid, then it's probably still going to be a double displacement reaction. So we're going to take this sodium and it's going to swap partners. So it's going to end up with the HCl, and our hydrogen is going to end up with the carbonate. So NaCl is going to be our product. And then our other one, for now, I'm going to call it H2CO3. Carbonate has a 2- charge, so we need 2 hydrogens to make a neutral molecule. All right, so let me erase some stuff so we can see if we're balanced. Okay, so we have 1 sodium on the right side, but 2 on the left side, so we need to balance that. So I'm going to make that a 2. So now we have 2 sodiums on both sides. We have 1 carbonate, so I'm going to leave that alone. Let's see about hydrogen. So we have 1 hydrogen on the left and 2 on the right, so I'm going to make that a 2. And now we have 2 Cls, we have 2 chlorines on both sides. So that is our balanced reaction, our balanced equation. 2 moles of HCl for every 1 mole of sodium carbonate. So when we are talking about these kinds of reactions, so what is the molarity of an HCl solution if 32 mils of the solution is required to react with 0.364 grams of sodium carbonate? So that sentence, that question, means how much is required to react. So we don't actually care about what is produced at all. We needed it to find our balanced equation, but we don't need it anymore. We don't care about the product. We just care about how much is required to react. So that means we want equal amounts of our two reactants. That is exactly how much is required. If we add any more of our acid, then we are adding more than we need. So that is not the amount that's required. The amount that's required is equal. So we want equal numbers of moles of our two substances. So we have 0.364 grams of this guy. And when we're given a molecular formula, we can use it to find the molar mass. And if we have a mass and a molar mass, we can convert to moles. So that's what I'm going to do. So we start with our mass, just like I showed you on the roadmap. So 0.364 grams of sodium carbonate. And we use our molar mass as our conversion to go to moles. So I'm going to look up the molar mass here and give it to you so that I, don't have to add it all up. So I found it to be 105.99 grams per mole. So you guys should be working along with me. You should have your notebooks out. You should be writing. Preferably, you could try to solve this problem before I do and then check your answer. But if you don't know where to start, you can just follow along. But you should have paper out. You should be writing it down, not just listening to this. All right. Anywho, that's going to get us 2 moles of our sodium carbonate. So that, and we want to get to a molarity of HCl. So I'm going to put in my next step right away, actually. So to get molarity, molarity is this capital M, which is moles per liter. So we need to get moles. Moles is part of this unit, so we need to find the moles of HCl. And we can do that with our balanced equation and our information about sodium carbonate. So our balanced equation says that there are 2 moles of HCl. That's our coefficient here. For every 1 mole, there's nothing written there, so that means it's a 1 of sodium carbonate. So 1 mole sodium carbonate, 2 moles of HCl. So if I plug that in my calculator and I solve, or I multiply 0.364 times 2, because I multiply across the top, and then I divide with the stuff on the bottom. So 0.364 times 2 divided by 105.99, that is going to get me to 0.00688 moles of HCl. All right, so we have moles of HCl, and we want to get moles per liter. So where can we find the number of liters that we need? In the question. The question gives us 32 milliliters, but we can easily convert that to liters. There's 1,000 milliliters in a liter. So I can do it this way, 32 mils times 10 to the negative third meters over, or sorry, not meters, liters over milliliters. Cancel out milliliters, so 32 times 10 to the negative third is going to be 0.032 liters. So we've got moles and we've got liters. We've got all we need to solve for concentration. So I'm going to erase a little bit here so we can do that. I'll just get rid of my products. Since we balanced our equation, we don't need it anymore. So we've got 0.00688 0.68 moles divided by 0.032 liters. And when I plug that in my calculator, I get 0.215 molar HCl. That is our concentration of HCl. So that is how you solve this type of problem. You look at what you're given. We were given two reactants, so we could write a reaction. We were given a mass of sodium carbonate with its molecular formula so that we could calculate moles. We could calculate the molar mass and the number of moles. And we were given a volume, so we could calculate molarity using moles and volume. So hopefully that made some sense to you. You can watch this as many times as you need and work it out yourself. You can change the numbers if you want to practice, but that is our final concentration for this reaction. We didn't need our products. We used our mole ratios of our reactants because we only cared about how much was required to react. We didn't care about what we were making. Okay, cool. I'm done with that one. Now, determine the volume of 1.250 molar HCl that is needed to neutralize 17.5 milliliters of a 0.875 molar barium hydroxide solution. Barium hydroxide and HCl, this is an acid-base reaction. So I'm going to do HCl plus barium hydroxide. It's an acid-base reaction, so it's a double displacement. So the barium's going to end up with the chlorine, and the hydrogen's going to end up with the OH to make water. So you're going to have barium chloride. Barium is a 2+, so we need two chlorides to balance it out, and water. So now we need to make sure it's balanced, which it's not. So there are, I'm going to get rid of all that. There are two chlorines on the right, but only one on the left. So I'm going to put a 2 here. So now there's two chlorines on both sides. There's one barium on both sides, so those are good. And now what do we have? We have two OHs and two Hs, so that makes two HOHs or two waters. So that gives us our balanced equation. But again, we don't actually care about this side of the reaction. Now that it's balanced, we don't care. We only need to know how much is needed to neutralize. That is exactly the same as the last problem. It's worded differently, but it's exactly the same. How much is required to react is the same as how much is needed to neutralize. We just use N's instead of R's, I guess. It's an acid-base reaction, so we also call that a neutralization reaction. So the amount that's needed to neutralize is the amount that's needed to react. So we want equal amounts of our two reactants. We don't want any more than that because that's not what's required. That is too much. We want exactly the right amount, exactly equal amounts of our moles of our reactants. So we want to find volume of HCl. We're given a concentration of barium hydroxide, and we're given a volume of barium hydroxide. So we use volume to go to moles with concentration as our conversion factor, if you remember that roadmap. So 17.5 milliliters, and we're going to use this molarity, so 0.875 moles per liter. That's what this capital M stands for again. This is not in liters, so I need to fix that. So if I convert to liters, you should know how to do this by now, but I'm going to move my decimal point over 3 places because that is what you'll get if you plug it into your calculator. Totally fine if you have to plug it into your calculator. Whatever works for you. Don't get stressed out by how to solve it. Just do it. So it'd be 17.5 times 10 to the negative third in your calculator, and you would get 0.0175. All right, when we have 0.0175, now it's liters, so liters cancel out with liters, and that'll get us to moles of barium hydroxide. And we want moles of HCl because we want to go from a concentration to a volume. And the thing that will get us there is moles of HCl because we want volume of HCl. So I'm going to find moles of HCl using our balanced equation. So our mole ratio tells us there's 1 mole of barium hydroxide because there's no coefficient there, so that's a 1, for 2 moles of HCl. All right, so this will get us to our moles of HCl. All right, and then we'll have one step after that. So let me do that step for you so that I don't skip steps like I did on my piece of paper right now. So I need to recalculate it so that I don't skip any steps when I'm showing it to you. Okay, so that comes out to 0.030625 moles of HCl. And now we want volume, and this is our conversion factor. Concentration is our conversion factor, and it's moles per liter. We want to cancel out moles, so we're going to flip it. We're going to put moles on the bottom of our conversion factor. 1.250 moles with liters on top. That's the same conversion factor, we just flipped it upside down. So we cancel out moles, and that'll be our answer. So 0.030625 divided by 1.25 gives us 0.0245 liters. Make sure you know your units. So it probably wants us to give our units in milliliters because we started with milliliters of barium hydroxide. So I'm going to convert it to milliliters of HCl. And to do that, I'm going to move my decimal place over. Sorry, I made a whole bunch of slides and ruined everything. Okay, sorry about that. Sorry about the squealing also. Anyway, move my decimal place over 3 spots if I can, which I obviously can't. Move my decimal place over 3 spots between the 4 and the 5. So 24.5 milliliters is our answer. We started with a volume and a concentration, went to moles, used our balance reaction to go to moles of our other chemical substance, and then we had moles and a concentration to go to volume. So this basically follows that bottom part of that roadmap that I showed you, volume to moles to moles to volume. Cool. All right, so that's a titration, an acid-base titration. It doesn't say anything about titration in the problem, but that's how you would do this experiment if you wanted to neutralize a barium hydroxide solution. All right, now we're going to do a different titration. So an analytical chemist weighs out 0.287 grams of an unknown monoprotic acid into a 100 milliliter volumetric flask and dilutes it to the mark with distilled water. Then titrates this solution with 0.320 molar sodium hydroxide solution. The titration reaches the equivalence point the chemist finds he has added 24.1 milliliters of NaOH solution. Calculate the molar mass of the unknown acid. All right, so calculating molar mass, that sounds scary, but we're going to break it down. It is not scary, I promise. What do we have? We are given a concentration of sodium hydroxide. We are given a volume of sodium hydroxide. What can we do with a volume and a concentration? We can calculate moles. And we are looking for the equivalence point. Equivalence point is where the amounts of acid and base, or the amounts of your reactants in general, are equivalent. So when we have equal amounts, so again, we're looking for equal numbers of moles of our, or at least stoichiometric amounts of our sodium hydroxide and our unknown acid. I shouldn't have said equal. The last two problems, it was actually not equal because we have a mole ratio here that is not 1 to 1. So they don't have equal number of moles. They have equivalent numbers of moles. That's what I should have said, and I apologize. Again, this one was also 2 to 1, so equivalent number of moles. All right. So we want our stoichiometric amounts of sodium hydroxide and this unknown acid. So we typically like to start with a balanced equation. We don't know what the acid is, but we do know something about it. We know that it's a monoprotic acid. That means that it only loses one hydrogen ion in solution. So monoprotic acids do this, whereas a diprotic acid would be something like this, where we'd have two hydrogens lost, and we'd have a -2 charge on our ion. So we don't have that. We have a monoprotic acid. So I'm going to call it HX. Okay, I'm going to get rid of this for now. So HX, oops, plus NaOH. We can pretend that it's HCl if we want to, because HCl is a monoprotic acid. It doesn't matter what we pretend it is, but we will know, all we will need to know here is that sodium hydroxide produces one hydroxide ion in solution. This produces one hydrogen ion in solution. They're going to pair up and make water. Our sodium is a +1 ion, and our X is a -1 ion because it's with a hydrogen. So we know it's a -1 anion. So when they combine, we get NaX. Easy enough. So that is our balanced equation. We don't need to worry about any coefficients. It's a one-to-one reaction because it's a monoprotic acid. So that one little word tells you a lot about the acid. Anywho, let's keep going. So we have a volume of sodium hydroxide and a concentration. That can get us to moles. So you start with volume, you use your conversion factor of concentration. So 24.1 milliliters. And we have our concentration, which is 0.320 moles over liters, because it's molarity. We need this one in liters. So again, I'm just going to move my decimal place over. So 0.0241 liters is equal to, or sorry, 24.1 milliliters is equal to 0.0241 liters. So now we have liters, liters cancel out. So this is moles of sodium hydroxide, but it's a one-to-one reaction. So this is also moles of HCl. Sorry, not HCl, HX. This is our moles of HX. We don't know what it is yet. So moles of sodium hydroxide cancel out, and we end up with moles of HX. So I calculated this, and I found that this gives us, that doesn't make sense. Okay, this gives us 0.2, no, there we go. I got it. Never mind. Uh, I should just calculate it instead of trying to read my handwriting. This gives us 0.007712 moles of our acid. And we want to know the molar mass. So let's think about molar masses. What are some examples of molar masses? Well, if we look on the periodic table, carbon's molar mass is 12.011 grams per mole. Oxygen is 15.9994 if we use our quiz periodic table, grams per mole. They all have the same units. Those units are grams per mole. We have moles, and we actually also have grams. It's in the question. 0.287 grams of the unknown acid. So we have the moles that reacted with the sodium hydroxide, and we have the mass that reacted with the sodium hydroxide. So we put them together to get the molar mass. We want units of grams per mole, so all I'm going to do is put 0.287 grams over the number of moles I just calculated, 0.007712 moles. And when I calculate that, I get 37.2 grams per mole. So that is the molar mass of our unknown acid. And it looks like a molar mass of elements or compounds that we've seen before, grams per mole. So you guys know how to do this, I promise. It looks really confusing, especially when there's a ton of words like this, but that's all. That's all you need to do. Find the moles and then use the mass that they gave you to calculate grams per mole. You didn't need this at all. So sometimes they give you extra information that you don't need. We don't care that there's 100 milliliters of the acid. That's just water. That's just diluted with water. The reaction happens with this amount of acid. Doesn't happen with 100 milliliters of acid. Happens with this mass of acid. And we want a molar mass, which doesn't have anything to do with this volume. Okay, cool. One more problem for you guys. Sorry this is taking a while, but I hope it's helpful. Finally, to measure the amount of iron in a certain type of iron ore, an analytical chemist dissolves 39.0 grams of the sample in strong acid and titrates it to the endpoint with 66.4 milliliters of 0.3500 molar potassium permanganate solution. And this is potassium permanganate. They just gave us the formula. The balanced chemical equation for this reaction, this is actually the net ionic equation for this reaction, is this big old equation. So the H that came from our strong acid, the iron came from our iron ore that we're analyzing, the manganate, the permanganate, sorry, came from our potassium permanganate solution. So when they react, they produce these things. They gave us the balanced equation, so we don't have to worry about balancing the equation. We can skip that step. So what kind of reaction is this, guys? You should be able to identify what kind of reaction this is pretty quickly. The easiest part to identify is that there's a 2 plus here on this iron ion. There's a 3 plus here on this iron ion. So neglecting anything else, this is a redox reaction because the oxidation number of iron changed. So the oxidation number of iron went from +2, because it's a 2 plus ion, a monoatomic ion with its charge has the oxidation number of that charge. And it's becoming a 3 plus ion, so its oxidation number is changing to a +3. So this is a redox reaction because we are seeing a change in oxidation numbers. If we want to go further, we can see what's being oxidized, what's being reduced, how many electrons are being transferred. So sure, why not? Let's do that. All right, so we know we're going from +2 to +3, but you want to take into account that there's 5 of those iron ions that are changing their oxidation number. So it's not a transfer of 1 electron to go from +2 to +3. It's a transfer of 5 electrons because 5 iron ions have to go from +2 to +3. So we do this, we do this +2 to +3 5 times. So there's a transfer of 5 electrons in this reaction. And we can tell what's being oxidized and what's being reduced without figuring out what the other thing is even. I'll give you a hint, it's the manganese, but you don't even actually need that to know what's being oxidized and reduced. Iron is going from +2 to +3. So it is losing an electron. It's becoming more positive. It's losing an electron. Leo the lion goes grr. Or oil rig. Both of those tell you that the O goes with the L, the R goes with the G. So loss of electrons is an oxidation. Iron is being oxidized. So iron is being oxidized. So that means that manganese is being reduced. So we actually know that manganese is changing its oxidation number by 5 electrons because the 5 electrons that iron loses, the 5 electrons that the 5 iron ions lose, one each, have to go somewhere. They go into manganese. So this is a +2, so this was a +7. And we could check that by calculating manganese and oxygen adding up to a -1. I want you guys to do that on your own time to practice. Remember, oxygen is almost always a 2 minus, so it's almost always a -2 oxidation state, oxidation number. So the sum of all of those oxygens and the manganese is going to equal -1 because it's a -1 ion. So you guys should practice that. You should find out that with 4 oxygens at -2 adding up to -1, we need a +7. So manganese starts at +7 and is reduced, so it goes down, to +2. It gained those electrons. So gaining electrons is a reduction. And if it's, so the thing that's oxidized is the reducing agent. The thing that is reduced is the oxidizing agent. Easy peasy. Remember, those two things switch. Um, those always go together. The thing being oxidized is the reducing agent. The thing being reduced is the oxidizing agent. Cool. That is our review of redox reactions in all of the forms that I can think of, other than doing this actual titration problem. So let's get to that. All right, so we want to do a titration problem. None of that really matters for this problem, but I thought it was good to review. Anyway, our endpoint, remember, endpoint is just the experimental equivalence point. So this, you should be familiar with this term because we talked about this a little bit in my last set of lecture slides, I think. So the endpoint is the experimental equivalence point. So still, we're talking about where we've got equivalent moles of our reactants. So 66.4 milliliters of 0.3500 molar potassium permanganate. So those two things go together. We've got a volume and a concentration. Volume and concentration can get us to moles, and that'll get us to moles of permanganate. Potassium permanganate, permanganate, same difference. There's one permanganate ion in potassium permanganate because there's no parentheses here. Okay, so let's find the moles of permanganate and then go from there. So 66.4, we've seen this a few times now. We're going to need this in liters. So I'm going to move it over, and that's liters. And 0.3500 moles per liter. Liters are going to cancel out, and we're going to get 0.01992 moles of permanganate ion. Potassium permanganate, permanganate ion, same difference. We have the same number of moles. So we have 0.01992 moles of permanganate ion. And then we want to look at our balanced equation to find our mole ratios. Remember, we're looking for the amount of iron in the sample, the mass percent of iron in the sample. So we want to look at iron. So there's no coefficient here. So that's 1 mole of permanganate ion for 5 moles of iron ion. This is a titration with an equivalence point. We only care about the reactants. We don't care about this anymore. That was just for balancing our reaction. Okay, so 0.0199, sorry, I did it again. 0.01992 moles of permanganate times this mole ratio. So 1 mole of permanganate ion for 5 moles of iron ion. In this case, it's iron 2 plus, but it doesn't really matter. So iron ion. So that's going to get us to 0.0996 moles of iron. All right, now is actually where it gets a little tricky. What do we do now? So I'm going to erase this up here. Oh, I can't erase it. Cool. So I'm going to erase this down here. All right. So I got a little bit of space, not a lot to work with. We've got moles of iron, and we want to find a mass percent of iron in the sample. We have a mass of the overall sample, and if we want a mass percent, we need the mass of iron in the sample to get the mass percent of iron in the sample. So how do we get a mass of iron from this number of moles of iron? Let's think. Moles, mass, what do we need to convert between the two? The molar mass. So we need to use the molar mass of iron from the periodic table to find the number of grams of iron in this sample. So that is 55.847 grams per mole. I put moles on the bottom, so now they cancel out. So that is going to be 5.56 grams of iron in our sample, and this is our total sample. So to get the percentage, we just divide by that number. So 5.56 grams divided by 39.0 grams, and the mass percent of iron in our sample is 14.3%. So remember, when you divide, you need to multiply by 100 to get it into a percent. So this was one type of problem that I actually took out of your homework because every time I looked at it, the question did not actually give me a redox problem like it said it was a redox titration. So I took it out because every time I checked, it gave me a precipitation reaction instead. So why call it a redox titration problem if it's not a redox titration problem? That's what I thought. So I got rid of it. But this is what it looked like. And I know a lot of you were having trouble with it. So this is how you would have solved it if I didn't get rid of it. And how you might have solved it if you already did it before I got rid of it. Sorry about that. I'm just going to do that to you all semester, I guess. All right, I'll see you guys tomorrow.